issue. Hello students, so please type in the chat box. Am I audible to you? Can you all see the screen? Okay, so I hope I'm audible to you, right? Now there is no issue. Yes, I'm live. Okay, great. Yeah, good morning. I hope all of you can hear me now. Is it? Yeah. Okay, fine. Chat box is fine. So welcome you all to this. Yes, so let us continue this session on internal viscous flows of fluids. Okay, so we have previously covered 5 lectures on this Abhyas course of fluid mechanics. On 5 lectures, we have covered the first 6 chapters: fluid and its properties, pressure and its measurement, hydrostatic forces. Then we have talked about buoyancy and flotation. Then we have seen differential and also the integral analysis of fluid systems. Basically, in differential analysis, we talked about all the derivative regarding things like, for example, acceleration, stream functions, potential functions, okay, streamlines. We have talked about all those things. And now in integral analysis, we are going to talk about this control volume. Okay, so we talked about this linear momentum equation, angular momentum equation, and all the things. Clear? So now we are going to talk about this internal viscous flows actually. Okay, so this internal viscous flows is actually one of the most easy and marks scoring topic of this fluid mechanics actually, because the number of or the model of questions that comes are basically very limited in this. And of course, if you have slight idea on fundamentals like Reynolds number, friction factors, pressure drops, then this is a very good chapter for you to easily score some marks here. Okay, so that's why let us, without any let us straight away start this problems on this internal viscous flows. Clear? So but before going straight away to this topic, okay, this is the first question. But before going straight away to this topic, I want to give you some little idea on basically some terms that we take into consideration when solving these questions. Okay, so let me first explain you to some light extent. So here what we'll do is, first we will talk about this coed flow. Just I'll give you the formulations, because we are going to use these formulations, because you see this expressions or the nomenclature that we are going to use here is not standardized in all the textbooks. Okay, so different books have different notations and all, but with respect to what notations I'm going to talk about these questions, I'm going to give you a hint in the first 5 minutes. Okay, so let us see. This coed flow is nothing but the flow between a fixed plate and of course this one. Okay, so if you see, this plate is fixed, for example, and if this plate is moving with some velocity, say u infinity, for example, okay, and let us suppose this clearance between these two is height h. Okay, so let us suppose the height between these two plates, or the distance between these two plates is actually h. Okay, now let us suppose there is some pressure gradient because of this which flow is happening, so minus dp by dx. So let us suppose there is some pressure gradient and it is a pressure driven flow. In that case, if you take this section as y, if you take this as your y direction, which is perpendicular to the direction of the flow, if this is y direction, then you have this result for this velocity at any location y is given by y by h plus alpha times of y by h times 1 minus y by h. So this is the velocity profile for this function. Means basically, if you have a fixed plate and if you have a movable plate like this, then at any location, let us suppose at some location y, if the velocity at this location is u, for example, then this u by u infinity is equal to y by h plus alpha times of y by h into 1 minus y by h actually here. Clear? Now what is this alpha value? This alpha is called dimensionless pressure gradient. Because I'm going to use this terminology to some extent. Okay, so dimensionless pressure gradient. And of course, how this equation is derived from the Navier-Stokes equation for the incompressible flows. So if you see the Navier-Stokes equation for the incompressible flows, we have the acceleration vector dv by dt is equal to body force vector minus del p by rho plus kinematic viscosity times del square operated on V bar. Okay, so this is a vectorial equation which many of you might have seen in a detailed fluid mechanics course. It's called the Navier-Stokes equation. So this equation, when you approximate for this condition of flow, you will end up with this velocity profile. Okay, so what is the value of alpha actually? Alpha is equal to h square by 2 mu u infinity times minus dp by dx. Okay, so this is the value of alpha, and of course in one simple case, in the case of simple co-ed flow, when this alpha value is 0, means if the pressure gradient is 0 actually, then in that case this second term gets eliminated and you have a linear velocity profile. Okay, means basically the velocity variation will be linear in that case. Okay, but depending upon the value of alpha, sometimes you can have various velocity profiles that comes into picture. But right now, whenever we are talking about means in problems, whenever we are talking about any situation with a fixed plate and a movable plate, then this is the nomenclature that I'm going to use, that this h is the distance between the plates and mu is the dynamic viscosity, u infinity is the free stream velocity, and h is the gap between the plates, dp by dx is the pressure gradient. Clear? Rahul, sorry, what is your query? Yes, definitely you can ask. How can we revise all the subject? Okay, definitely I can see only this thing. I'll tell you, I'll give you some short things to how to remember the subject, how to practice the questions and all these things. Okay, clear? Meanwhile, so now first of all let us see this thing. So this is h alpha is equal to h square by 2 mu u infinity times minus dp by dx. So once you have this velocity profile, then you can calculate whatever you want. You can calculate discharges, shear stress, whatever you want, you can always calculate. Similarly, if you have a plane Poiseuille flow, means flow between two parallel plates which are fixed. Okay, so if you talk about this plane Poiseuille flow, I'm just giving you some hints so that we use this terminology. Okay, so plane Poiseuille flow. If you take this plane Poiseuille flow, then in that case you have two fixed plates like this. You have two fixed plates. If these are fixed plates, then and let us suppose the gap between the plates is symmetric about this guy. Okay, so this line. So now if you see my coordinate system, what I am defining is here 0, x and y, for example, in this direction, then we call this distance as h in our analysis. Okay, and also this distance as h, small h, because because if I take h normally it will be h by 2 and all. So to eliminate that h by 2 and all, I am taking h and h, so that the total gap between the plates is actually 2 times of small h. Okay, so in this case, if you want the velocity profile at any location, u is equal to, at any location y, this value is given by h square by 2 mu times minus dp by dx into 1 minus y by h whole square. Okay, so this will be the velocity profile in this situation. Okay, so in this case where mu is the dynamic viscosity and all, and both the plates are fixed, so if you want velocity of layer at any location y, say for example at this elevation y, then if you keep the corresponding value of y, h value is known to you, mu is known to you, dp by dx, normally if you know the pressure gradient, you can calculate the velocities. Okay, so basically when I am telling you h is nothing but half of the gap between the plates. Similarly, if I talk about, and here in this case, the average velocity by maximum velocity, umax is equal to 2 by 3. Okay, so this value is actually equal to 2 by 3. So average by maximum velocity is equal to 2 by 3 in this case. And similarly, if you talk about this Hagen-Poiseuille flow, if you talk about this Hagen-Poiseuille flow, which is basically flow through a pipe. Okay, so if you talk about this Hagen-Poiseuille flow through a pipe, normally in detailed course I should have all these things, but since this is a quick problem solving session, we are just trying to recollect the things. Okay, so let us suppose if this is a pipe, for example, and let us suppose this is the axis of the pipe. If this is the axis of the pipe, then if you measure radius in this location, in this direction, so obviously radius is measured in this direction, it's smaller, and of course if the total radius of the pipe is capital R, for example. Okay, so this is radius of the pipe, then the velocity profile at any location is given by, let us suppose if this direction is z direction, if this direction is z direction, means along the flow if you take z direction, because in polar coordinates, so if you see, then we'll get this u at any location is equal to, means u at any radius is given by r square by 4 mu times minus dp by dz, means pressure gradient in the direction of the flow, into 1 minus small r square by capital R square. Okay, so this velocity profile has to be known to you in general if you want to solve some questions, because we are going to use these terminologies, small h, small r, all these things in the upcoming questions. So that's why I'm giving you the normal internal viscous flows. We generally discuss 3 types of flows, actually 4, but the fourth one is normally in XC, not for mechanical in general. But if you see, we have this Coet flow, plain Poiseuille flow, and also this Huygens-Poiseuille flow. Okay, and one good point I would like to give you here at this location is the total discharge to the plates is actually equal to u infinity times h into 1 by 2 plus alpha by 6. This is the total discharge between the plates actually at any given instant. Okay, now depending upon alpha being positive or negative, the velocity profiles will actually exist. Okay, if alpha is equal to 0, then I told you, if alpha is equal to 0, your velocity profile will be something like this. Means at a section, if you see the velocity profile will actually increase like this. Okay, so the velocity profile will be increasing like this. The velocity profile will be increasing like this. Okay, so the velocity profile increases, and let us suppose if u infinity, means if alpha is actually more than 0 and all, then in such cases you get a velocity profile like this. For example, alpha is equal to 2 or something, means at some location in the flow you can have a velocity which is higher than this u infinity, because from the first chapter your basic intuition will be like, as this y direction increases, the velocity will increase linearly, and this will be the location of y at which velocity is maximum. But depending on this pressure gradient, actually in viscous flows you can have a velocity which is higher than this u infinity. For example, if you see the velocity at this location, then this location velocity is definitely higher than this u infinity, you can see. Okay, so that's how these 3 things are basically important for us to understand this viscous flows. Clear? Normally in class we would derive this using the Navier-Stokes equation, how this velocity profile came, similarly how these 2 velocity profiles actually came. Okay, and in this case, if you see, I would like to give you one understanding. U average by U max is actually 1 by 2. Okay, so in this case average velocity is half of the maximum velocity. So these points, if you can remember, we'll quickly go for solving the questions. Okay, so shall we start the questions? So please type in the chat box. Shall we start the questions? Did you get understanding on this? So if equations of coveted flow, how to know if alpha is 0 or not? Normally if they depend on this pressure gradient value, it depends on this pressure gradient value, because for any type of fluid and any plate movement, definitely h, u, mu, u infinity, all this will exist. But let us suppose if the pressure gradient is 0, in that case then definitely we have the 0 pressure gradient, so alpha value is 0. Okay, so normally how to identify physically is, let us suppose if I am intentionally applying some force F on this plate and moving, then the flow is happening because of the force I applied, but not because of the pressure gradient that is coming into picture. Okay, so that's how we actually decide if the change in pressure is not responsible for the flow, we call them as some other, basically inertia driven flows or some externally applied flows and all these things. Okay, but actually if the flow is because of this pressure gradient, then we call them as pressure driven flows. Okay, that's how basically we decide whether alpha value is 0 or a non-zero value. Clear? So this is a quick understanding before we start the problems. Okay, so let us straight away solve the problems. So this is the first question. So let us try to solve this question. First question: water is discharged through a 150 mm diameter pipe fitted to the bottom of a tank. A pressure gauge fitted at the bottom of the pipe, which is 10 meters below the water level, shows 0.5 bar. So this is actually showing 0.5 bar. Assume the friction loss as 4.5 V2 square by 2g. The flow rate is dash in liters per second. Okay, so they are asking you, okay, if alpha greater than 0 or less than 0 or equal to 0, in all the cases fluid flows in between the plates. Okay, but what is responsible for the fluid flow is that decides the value of alpha actually. Okay, whether it's 0 or not. Clear? So now let us see here. In this case they are asking you that there is a tank, basically there is a tank like this. So there is a tank like this, and at the bottom of the tank you have a pipeline fitted. At the bottom of the tank you have a pipeline which is fitted like this, for example. Okay, You have a pipeline fitted. Now if you have a pipeline fitted, now let us suppose if this is the free surface of the fluid in this. Let us suppose if this is the free surface. Okay, free surface. So there is some fluid which is flowing actually like this. Okay, now what's happened? They have fixed a pressure gauge here. They have fixed a pressure gauge here, for example. Okay, so there is a pressure gauge like this. So this pressure gauge is at a location of 10 meters below the free surface. Means basically if you take this elevation, if you take the elevation of that point from this location, then this value is actually 10 meters. Okay, so this value is actually a 10 meters. This value is 10 meters. Okay, so now if this value is 10 meters, they are asking you what could be the discharge value. Okay, so what is the value of discharge, flow rate in liters per second? So basically if you know the cross section of this, let us suppose if this is a pipe, so diameter is given. So if you see, discharge value is equal to pi by 4 d square into velocity through this section. Okay, so if you call this V for example, or V2 for example, let us call this location 1 and this is location 2 for example, so let us call this is V2. So this is how we get the discharge value. So let us see, of course diameter of the pipe might have been given to you. So if you see a pressure gauge to a 150 mm diameter pipe, so pipe diameter is known to you. Now the only thing that you should know is velocity. So how you identify that velocity? Look, we can see, so basically this is the case, a pressure gauge fitted at the bottom of the pipe which is 10 meters below the water. Assume the friction loss as 4.5 V2 square by 2G. Now if you apply Bernoulli's equation at these two locations, whenever we have applied Bernoulli's equation in yesterday's case, we didn't consider any friction actually, so that's why we assumed that there are no losses. But actually whatever is the total head available here, that head available is equal to head available at this location plus the losses during the flow. Okay, so that's why if I call this total head at H1 and if I call this H2, then definitely from energy conservation, means basically Bernoulli's equation, from energy conservation, which is basically the Bernoulli's equation, if you see, H1 is equal to H2 total head available plus losses that happened, correct? So what is H1? P1 by rho z plus V1 square by 2z plus Z1 is equal to total head at this location 2 is P2 by rho g plus V2 square by 2g plus Z2 plus head loss. So head losses are given here, the frictional loss as 4.5 times of V2 square by 2g. So 4.5 times of V2 square by 2g. This is the value. Okay, now let us see what we can do with the help of Bernoulli's equation. So at this location 1, this is open to atmosphere, and at this location 2, whenever the outside atmosphere is the normal atmosphere, this gauge is showing 0.5 bar, which means one thing is very clear: if P1 is P ATM local and P2, then definitely P2 is nothing but P ATM local plus 0.5, correct? Because it is showing 0.5 bar, water level shows 0.5 bar. So if you see, this is 0.5 bar actually. So now if you apply here, then you can take this value P1 as 0 for example, and this P2 can be taken as 0.5 bar in pascals if you hit 0.5 into 10 to the power 5 pascals. That's how the difference between these two, because if you see, even if you hit PATM plus this value, PATM gets cancelled on both sides. That's how. Okay, so whenever we are rating gauge pressures, if one of the pressure is atmosphere, you can make it 0. Next, coming to this location, let us suppose it's a big tank, then definitely the velocity of these particles which are here is very low, so the tank level comes down very slowly, which means the velocity of the particles at this free surface is actually very low. So that's why we are taking this V1 is also 0. Next, if you see, if you take this as the datum, Z1 value is plus 10 because it is 10 meters above here. Okay, and Z2 value is 0 because this point is on the datum again. Okay, so these are the quantities that we have actually. So this implies, if you simplify this equation, 10 is equal to 0.5 into 10 cube, 0.5 into 10 cube by rho g. What is the fluid here? Tell me. The fluid given is water, so nothing is mentioned, so let us take 10 cube into g plus V2 square by 2g plus 4.5 times of V2 square by 2g. So total 5.5 times of V2 square by 2g. So if you simplify this, we'll get the value of V2, and if you multiply here, you'll get it discharge. Okay, so let us simplify. 10 cube and 10 cube gets cancelled, of course, and then this implies 10 minus 0.5 by G into 2G. So 2G times by 5.5. 2G by 5.5 times of 10 minus 0.5 by G. So this is the value of V2 square, correct? Because if you see, 10 minus this 0.5 by G comes left side, and this 2G by 5.5 gets a multiplication here. So if you simplify this value of V2, let us see what will we get for the value of V2 in meters per second. Okay, so let us calculate this value. 10 minus 0.5 by G, which is 9.81. Okay, so this value 9.948 into 2 into 9.81 by 5.5 into 2 into 9.81 by 5.5. So if you simplify this, 35.49, and you need to take a square root of this. So if you take a square root, 5.957 meters per second, correct? So this is 5.957 meters per second. So if you want to convert this 5.957 to units, we have taken bar. They have given you bar, right? So 0.5 bar. So what is 0.5 bar actually? Any mistake? Any units we have made mistake? So please tell me. This is 10. This is in pascals. Okay, here 10 power 5 it should be there, correct? So here this is 10 power 5. Okay, fine. So if this is 10 power 5, then here the value changes. Yes, 2. So if you take 10 power 5 here, then of course 10 square remains here. Okay, so 10 square into 500 is 50 by G, correct? Okay, so I think that's what you have done the calculation. So please type in the chat box. That's it, right? So 10 square into 0.5. Yes, correct? So now it's fine. So please type in the chat box. 0.5 into 10 square is 50 divided by G. Yes, because this has to be in Pascal. So 0.5 into 10 power 5 has to be substituted. Okay, normal inflow we have substituted in kilopascals, but anyhow, this is the correct answer. So let us calculate this value. 50 by 9.81. This value, this has to be subtracted from 10. So if you subtract this from 10, then multiply it with 2G by, so 2G by 5.5. So this is V2 square. So if you take a square root, 4.1822. 4.1822 meters per second, correct? So 4.1822 meters per second. So now if you substitute here Q times of pi by 4. Now what is the diameter of the pipe? You have seen the diameter of the pipe is 150 mm. It's given here 150 mm diameter. So 0.15 whole square times V2. So V2 value is 4.1822. So these many meter cube per second is the answer. Okay, so this is the value in meter cube per second. So let us calculate this value. This 4.1822 is as it is here into 0.15 square into pi by 4. So if you simplify, 0.07390, 0.07390, but they are asking you the value in liters per second, correct? This is in liters per second. So you know 1 liters per second is equal to 10 to the power minus 3 meter cube per second. So if you simplify this, then if you want to convert meter cube into liters, you need to multiply with 1000. Okay, so if you multiply this with 1000, you will get 73.90 liters per second. That's it. Okay, so this is the discharge that is flowing through this pipe. Clear? So basically one Bernoulli's equation and one continuity means basically calculating the discharge gives you the answer for this question. Is this clear to you? So please type in the chat box. Did you all understand how I have formed this diagram and how I have applied the Bernoulli's equation? Yes, everyone. So please type in the chat box. Abhimanyu, you know, Fateh, all of you, Ramanujan. So please type in the chat box, guys. Is this clear to all of you? Yes. So now the correct answer is of course 73.90 liters per second is the correct answer. Okay, so this is how we have achieved the answer, basically applying the Bernoulli's equation between these two locations and then writing the velocity V2 as multiplication of this to get the discharge value. Clear? So let us go for the next question. So let us go for this question. Second question. A 100 mm diameter pipe branches into a 80 mm diameter and 120 mm diameter pipes and reunite into a 100 mm diameter again pipe as shown in figure. The 120 mm diameter as shown in figure, so this is the figure. Okay, so basically there is a 100 mm diameter pipe. It got branched into 80 mm and 120 mm diameters, and finally again it got converted to 100 mm diameter. Okay, so now let us see. The 120 mm diameter pipe has a valve such that the two pipes carry the equal discharges. So obviously by adjusting this valve, you can make sure that the discharges flowing in these two is actually same. The loss of head in the valve is K times the kinetic head in the pipe. Okay, so basically because of this valve there is some friction, because this valve is a restriction in the flow. So because of the friction there is some loss of energy in this valve. Okay, so whenever there is loss of energy in the valve, for F is equal to 0.005 for each pipe. Of course for both the pipes it is same. Two pipes are each 25 meters long. The coefficient value K is, so it's given the loss in the valve is K times of the kinetic head. So they are asking you what is the value of K. Okay, so let us see what is the value of K here. So first of all, if you see, these two pipes are parallel in combination, correct? So these two are parallel pipes, so the parallel flow is constant. So let us suppose if some fluid at some energy 1 starts here, then let us suppose all over this pipe this fluid attained this location, and all over this pipe also this fluid attained the location. So here if you see again at this location, this for this flow the two fluids should have same heads. That means if there is any loss in friction, then definitely the head loss in this parallel sections should be same. That's why in any parallel flow the head loss is same in both the in all the branches actually. Okay, so let us see head loss in one. Since the pipes are parallel, you can write, since the pipes are parallel, let us write this. Total head loss in 1 is equal to total head loss in 2. So what is the head, you write head loss in 1, head loss in first pipe is equal to head loss in second pipe. Let us say head loss in second pipe. So in first pipe of this 120 mm diameter, the loss is due to two portions. First thing, because of the motion in this pipe, obviously there is some friction in the pipe, so there is some head loss. And second thing, it's given at this valve also there is some friction loss or the head loss, and that head loss is K times of the kinetic head, correct? So what is kinetic head in this case? V1 square by 2G, correct? This is the kinetic head. So the valve loss at the valve, so HL at the valve is equal to V1 square by 2G times K. There is some constant K. Okay, so let us see what comes out. So head loss to the first section means basically to this first pipe is equal to F1 L1 V1 square by 2G D1 plus this is the head loss basically due to the friction, and of course due to the valve it is K times of the kinetic head. So K times of V1 square by 2G. And this is equal to head loss to the second pipe. Here there is only pipe flow, so because of the friction there is some head loss. So F2 L2 V2 square by 2G D2 is what you have. Okay, so F2 L2 V2 square by 2G D2. So now if you simplify the things, first of all let us try to write what is V2 value in terms of V1. Given discharge in both the pipes is same, correct? So Q1 is equal to Q2, because it's told you that this valve has adjusted in such a way that the flow to both is same, means the equal discharges. So this gives you pi by 4 d1 square v1 is equal to pi by 4 d2 square v2. Okay, so if you cancel this pi by 4 and pi by 4 for example, then v2 can be written as d1 by d2 whole square times v1, correct? This I can replace here. So if this I can replace, and at the same time this v1 I can replace with, you know, let us see what we can replace with. Okay, so this implies f1 l1, this v1 square can be written as, okay, let us write v1 square as it is, by 2g d1 plus k times of v1 square by 2g is equal to f2 L2 by 2G D2 into this V2 square. V2 square, if you add this in this coefficients, so D1 by D2 whole to the power 4 into V1 square, correct? We can write this V2 square in terms of this value. So if you write this V2 square in terms of this value, because V2 is equal to D1 by D2 whole square into V1, so if you simplify the result, this V1 square gets cancelled in all the terms. Okay, so because if you see discharge is same, so because of the same discharge condition we have at this condition, so if you cancel out all the V squares here, now let us see, plus K is also there. Okay, so now if you see this 2G is also a constant in all sides, you can delete it. Okay, so now if you delete the things, we have this K value is equal to F2 L2 by D2 times of D1 by D2 whole power 4, D1 by D2 whole power 4 minus this term F1 L1 by D1 on the other side. So F1 L1 by D1. Now if you see, they have given you both pipes have same diameter, each 25 meters long, and of course the kinetic head and F is equal to 0.005 for each pipe. So if you see, this friction factor and lengths are actually same in these two cases. Okay, why Q1 equal to Q2? Because here they have told you the wall. Okay, here if you see, it is told that the 120 mm diameter pipe has a wall such that two pipes carry the equal discharges. Okay, so because of this line, the two pipes carry the equal discharges, we have made sure that the discharge in both the pipes is actually equal. Clear? Okay, so now because of this we are doing this. Okay, now FL is same in both the cases. So if FL is same, then you can write some things. K value is equal to FL D1 by D2 whole to the power 4 times of 1 by D2 minus 1 by D1. That is the value of K. That's it. Okay, so this is the total value of K. Now you have all the numerical values. If you see, D1 is 120 mm, D2 80 mm. Okay, and what about F and L? They are given to you. F is 0.005 and L is 25 meters. So you have all the four values for the substitution here. So if you substitute, you will get the answer. Okay, so let us see what is the value here. So let us see here. If you substitute, K is equal to FL, F 5 into 10 to the power minus 3, L 25 divided by FL by, okay, by is nothing is that D1 by D2 whole power 4. So D1 by D2 whole to the power 4 into D1 by D2, D1 120 by 80 whole to the power 4 into 1 by D2. 1 by D2 is actually 1 by 80 mm, means 1 by 0.08 minus 1 by 120, so 0.12. So this is the value which gives you the constant K. Okay, so if you simplify, you will get the value of the constant K. So let us see basically what you will get. Before that, if you slightly make the simplification, 40 table will cancel 2 times, 40 table will cancel 3 times. Okay, so anyhow, let us do this calculation. So 1 by 0.008, sorry, 0.008, right, 80 mm, so 0.8, 1 by 0.08 minus 1 by 0.12. Okay, so we have these values. So 4.166 into 3 by 2 is 1.5, 1.5 whole power 4, so into 1.5. okay, so let us see, let us open a bracket, 1.5 power 4. So this is the value multiplied with 25 into 5, again 125 multiplied with 125, and you have a 10 to the power minus 3 here. So that means this value of K is actually 2.636 because of this 10 to the power minus 3. So K value is actually 2.636 is the correct value. So the loss at the valve is 2.636 times of this kinetic head loss. Okay, so this is the kinetic head loss here, and kinetic head loss is given by K, this V1 square by 2G, this is given by K times of the kinetic head. So loss at valve is given, so K value of this analysis gives you 2.636 as the correct answer. Okay, so 2.63, right? Did you all get 2.63? Okay, 2.63, correct? So then I think we have made some decimal here in the calculation. So 2.57842 to 2.9720. Okay, so the decimal comes here. So 2.5784 to 2.9720. Okay, so 2.6 is the correct answer. 6567. Sorry, 636, correct? So we got 2.636. Yes, 2.636 is the correct answer for this question. Did you all get 2.636? So please type in the chat box. How many of you have got this? Yes, Ramanujan, good. So how many of you have got this? 2.636 here. So how many of you got this 2.636 in the calculation? So because we have seen, everything is simple here. Okay, so just we have equated the losses, but loss at this first section is equal to sum of losses of these two, one due to the motion of fluid in the pipe, and second due to the loss at the valve basically. Okay, so F1 L1 V1 square by 2G D1 plus this quantity is equal to F2 L2 by 2G D2 times this value, and we have converted this V2 in terms of V1 basically with this understanding. So V2 is equal to D1 by D2 whole square times V1. So if you replace here, we'll get D1 by D2 whole power 4 times V1 square, and if you see V1 square gets cancelled and 2G is common denominator, so if you cancel them, then we got F1 L1 or K value. If you see, the K is the only value here, so K is equal to F2 L2 by D2 times this quantity minus F1 L1 by D1. Now it's given F and L are same for both the pipes, so FL, if you take common, this FL D1 by D2 whole power 4, if you take out, okay, here we have taken out, correct? So I think there is some problem here, because if you see, this D1 by D2 whole power 4 is not in this location, correct? So if you see, let us try to simplify it like this as usual. So let us try to simplify this. If you take only this FL as common term, if you take only this FL as common term, if you take only this FL as common term, then D1 power 4 by D2 power 5 minus 1 by D1 is the value. So if you simplify, D1 is how much? D1 is 1.12. Okay, D1 is 0.12 meters and D2 is 0.08 meters. So D1 is 0.12 meters and D2 is 0.08 meters. So if you simplify this, let us simplify once again. D1 power 4, D1 power 4 divided by D2 power 5. Okay, so divided by D2 power 5. So this is the value minus 1 by D1. So 1 by D1 is 0.12. 1 by D1 is 0.12. So this is the total value, 54.947 multiplied with FL. So multiplied with FL, so into 5 into 25. So to this we need to take a 10 to the power minus 3, correct? So please tell me. We are getting 6.86, right? 6.868. So into 10 power minus 3, we got 6.868. We are getting, correct? 6.868. Yes, we are getting 6.868 if I'm not wrong, correct? If you check the calculations, 6868 into 10 to the power minus 3, so 6.868, correct? Yes, you all got 6.86. Fine then. Okay, yes, 6.86 is the correct value for this question. Okay, so because if you see, we have done some small calculation here, because basically we have taken D1 by D2 whole power 4 as common, which is not actually here. Okay, so that's why we got a different answer. So K is equal to 6.868. Okay, so this is the correct answer for this question. I thought my calculations are incorrect. Yeah, it happens sometimes. Even you see, I have missed this D1 by D2 whole power 4. Calculation mistakes can happen, so we need to be a little careful. Okay, so from next time we will solve step by step clearly, because many times I write direct expressions which gives me this fantastic results like this. Okay, I'll tell you one thing. When I've got all India rank 40, I've checked the response sheet. Obviously after exam, you'll get the options that you have kept in the exam, you'll get the response sheet. So I have made a calculation mistakes of 8.66 marks. Okay, so 8.66. My marks at that time was 75 in XC. Paper was little high at that time, so it is 75, and 77.5. This marks got all India 20. Okay, and I stopped at 40 after committing this calculation mistakes. Okay, so that's why please make sure that when you're doing calculations, even I have to learn along with you. Without this direct calculations, cancellations can sometimes be dangerous. So we'll go in a step by step way. Okay, so did you all get 6.86? So tell me, how many of you got 6.86? Bhavya, Tripathi, Ramanujan, Purnab, all of you? Correct. So this is 6.868. Okay, so 6.868. We'll clear this and we'll say 6.868 is the correct answer here. Okay, so 6.868 is the correct answer. Okay, so let's go for the next question. Radius of a pipe is varying as r is equal to a into e to the power minus 0.0009 x, where a is in meters and x is in mm. Okay, so x is in mm. Ratio of Reynolds number between 2 points which are 2 meters apart is approximately dash. So let us suppose you have a pipe, but this time pipe is not of uniform diameter, it is of some different diameter like this, or generally it is a minus function, so like this. So let us suppose the pipe cross section is like this, it's some random cross section as per this exponential function, okay. In general, if you want exactly mathematically, I will give you, this is the pipe, okay. So with x, if you see, this is the beginning of the pipe, for example, this is the beginning of the pipe, means at this section you have the inlet, and at this section you have the outlet basically, okay. So at this section you have the outlet. So whenever you have the inlet and outlet, so this radius at any location, at this location if you want to calculate the radius value, at this location if you want to calculate the radius value, this r is given by a into e to the power minus 0.009 times of x, clear. So that's we have a into e to the power minus 0.009 times x. Now they're asking you, if you take 2 points in the flow, if you take 2 points in the flow, first point, say second point, and let us suppose that gap in between these two is 2 meters. The gap in between these two is 2 meters, for example, okay. If the gap between these two is 2 meters, then what is the ratio of the Reynolds numbers, okay. Solving series on extra topics of XEFM, yes, definitely I'll do that, okay. Once this course is done, then we'll plan that and we'll take the sessions, okay, no issue. So now let us see, this is 2 meters, so they're asking you, if you take this Reynolds number at these two locations, Reynolds number 1 and Reynolds number 2, Reynolds number 2, so they are asking you what is the ratio of these two Reynolds numbers, okay. So basically if you want to see the relation of this Reynolds number with respect to this radius, we can observe like this. See, Reynolds number is basically equal to V average into d at one section divided by nu, kinematic viscosity, correct. So V average into dh by nu, dh is called hydraulic diameter, which is basically 4 times of cross section of flow into divided by the wetted parameter, and similarly here this is kinematic viscosity. So now if you see, this is a pipe, single pipe, so whatever is the discharge that is going here, definitely the same discharge should also cross this location, correct, yes or no, because inside there is no cavities or something, so that the flow cannot go out or something, okay. So whatever is the discharge that is crossing this point at this section, same has to be the discharge that has to cross at this section. So that's why if you equate discharges at these two locations by assuming here the radius is r1, here the radius is r1, and here the radius is r2, for example, okay. So r1 and r2, r1 and r2 is the radius here, okay. So if r1 comma r2 are the radius, then try to understand, if you see discharge at section 1 and discharge at section 2, both are same, so this implies pi by 4 d1 square into V average at section 1 is equal to pi by 4 d2 square into V average at section 2 actually here. So pi by 4 gets cancelled obviously, so you know V average at section 1 by V average at section 2 is equal to d2 by d1 whole square. This is what you have, okay. So let us substitute here, Reynolds number at location 1 divided by Reynolds number at location 2. Since the fluid is same at both the locations, kinematic viscosity is property of the fluid, so if you eliminate this, V average at 1 divided by V average at 2 into d1 by d2 is what you have actually, okay. So if you see d1 by d2, so this can be written as, if you replace this v1 by v2 with this d2 by d1 whole square, so d2 by d1 whole square into d1 by d2 gives you 1 d2 by d1 value, okay. So that's how the Reynolds number at these two locations is actually equal to the ratio of these two diameters, okay. So let us see, Reynolds number at location 1 by Reynolds number at location 2 is equal to radius d2 by d1 can be written as r2 by r1, because if you see this is a 2 combination, so this can be written as r2 by r1. So ratio at these two locations is actually equal to a into e to the power minus 0.009 x2 divided by a into e to the power minus 0.009 times of x1. So if you cancel these terms, if you cancel this a, then you can observe e to the power, this is a power m by n format, okay. So this is a power m by n, so if you simplify a power m minus n, so minus 0.009 times of x2 minus x1. So given these 2 points are at 2 meters distance, okay. So but x when you are trying to substitute, you need to substitute here in mm, because in this formula this x value is given in mm. So x2 minus x1 difference is 2 meters, which means 2000 mm. Clear? So if you see, this implies Reynolds number at location 1 by Reynolds number at location 2 is equal to e to the power minus 9 into 10 to the power minus 3 into 2 times of 10 cube. Correct? One more 0 is also there. 3 zeros are there. Okay, so 10 to the power minus 4. Okay, so 10 to the power minus 4 here. 1 2 3 4 times of x1, 1 2 3 4 times of x2. So which means one more 0 comes here. 1 2 3 9. Okay, so that means this turns out to be a 4. Okay, so this value is 4. So now if you simplify this, we'll get this as 10 to the power minus 1. So this is e to the power minus 0.18. So this is the ratio. So let us see what is this value here. Okay, so how can I know first by lost or lost by first? No clear in this question. Okay, basically they have asked you the ratio of 2 points which are 2 meters apart is approximately. Okay, so basically, okay, if they are not given, I'll just write this re1 by re2. Okay, but normally whenever you are taking first divided by the second is always the case by default. Whenever you take ratios, if I say the ratio at 2 points, first point by second point is what you need to consider by default. Okay, Abhimanyu, but generally they'll mention, but in this question somehow they missed. But actually if you see, we actually tell you that if I tell you the ratio between 2 points, then first point is at first point divided by the second point. Clear? So how discharge is equal to same, because the flow is actually, if you see, if this is incompressible flow, means basically there is some fluid, water or something, if it is flowing, then in that case the density at this location and density at this location is equal. For example, in case of water or something, then whatever is the mass that is flowing here, same mass should cross this section, because this pipe cannot hold any fluid. Okay, so that's why in steady state what happens, whatever is the mass that is entering the pipe or entering this section should actually leave this section. Clear? Okay, so that's why the mass leaving at this section should be same as the mass leaving this section, so that's why they are equal. Okay, so now if you see this, so e power minus 0.18, so let us see, minus 0.18 exponential, so 0.83527. so inverse of this gives you, sorry, e to the power minus 0.18. correct? So e to the power minus 0.18. let us see, minus 0.18. so if you see, exponential of this value is 0.835, and yes, so this is the value of the Reynolds number. Clear? We have all the things, d2 by d1 and all. So this is a into, this is 2 9s are 18, so 18 into 10 to the power minus 1 with a minus sign, so minus 0.18. Clear? For yes, from the continuity equation we have observed this. Okay, so this is 2 9s are 18, so 1.8. yes, 2 9s are 18, so 18 times 10 power minus 1, so this is e power minus 1.8. so if you simplify this, minus 1.8 exponential of this, okay, 0.16529. so this value is 0.16529. okay, so normally that means this Reynolds number second is highest, so this implies Reynolds number at location 2 by Reynolds number at location 1 is actually inverse of this. So if you take 1 by x, 6.0496, 6.0496 is the answer for this. Okay, yes, this is 2 by 1 and this is 1 by 2. Since nothing is mentioned, actually both the answers will be actually given correct here, but generally if they ask you 1 by 2 or 2 by 1, we'll go for accordingly this value or this value. Okay, is this clear to you? Fine. Okay, since they did not mention 1 and 2, both can be written as the correct answers. So in general, in examination and all, they give you one of these values. Very strictly they'll ask you location 1 by location 2 or location 2 by location 1. So depending on that, you can enter one of these values. Okay, 0.165 in the first attempt. Okay, basically you have taken this value, Reynolds number at location 1 to Reynolds number at location 2. Okay, let's go for this question. Consider two types of drinking straws, one with a square cross section and cross sectional shape, and other type the typical round shape. Okay, means basically the normal straw that you have, the cylindrical one, the circular straw. The amount of material in each straw and length of the perimeter of the cross section of each shape are same. So let us try to understand this question. There are two straws. One is with a square cross section and another with a circular one. Okay, so this is with a circular one. Okay, so let us suppose if the square cross section has a side A, and let us suppose here the diameter is D, for example. It's given, what is given here? The amount of material in each straw and length of the perimeter of the cross section of each shape are same. So the perimeter, length of the perimeter here means 4A, and this is equal to pi times of D. These are same. So basically A can be written as pi by 4 times of D. Okay, so this is what you have. The relation between A and D is this. Okay, so now what they are telling you. Assume the ink is viscous enough to ensure laminar flow and neglect gravity. The ratio of the flow rates Q dot round by Q dot square means if you take the discharge in the round one to the ratio of discharge in the square one is what? So what is this value? They are asking you. The discharges in these two straws is what value? That's what they are asking. So the straws for a given pressure drop per unit length is same. Okay, so if you see the ratio of flow rate to the straws for a given pressure drop per unit length is dash. Okay, so they are asking you, right? So they are asking you the ratio of flow rates to the straws for a given pressure drop per unit length is same. Okay, I think the word same is missed here. So is same. Okay, so for square cross section, F into REH means the Reynolds number is equal to 56.9. For round shape, F into REH is equal to 64. Okay, so they have given you for square cross section, the friction factor multiplied with the Reynolds number is 56.9. So F into REH, Reynolds number is equal to 56.9, and this F into this Reynolds number for the circular cross section is how much? 64 is given. Okay, 64. Now they are asking you this delta P is same. Okay, so how we try to analyze this? So delta P by L is same actually. Okay, so delta P by L is actually same for this square and also for this round one. Okay, so delta P. So basically how you calculate this delta P? Length of the straws is length of the straws, I think they have given you the same value. Okay, typical round shape, the amount of material in each straw and the length and the perimeter of the cross section of each shape is same. Okay, so length is also same. So now means lengths are same, that means the pressure difference is actually the same value. So basically how we calculate the pressure difference? This is equal to rho F G into this head loss, which is F L V square by 2GD. 2G. Okay, let us see, this is the hydraulic diameter. So let us keep this value here. So the head loss in this case, okay, so FL V square by 2G DH is equal to here rho FG into FL V square in this case by 2G D. Of course the diameter in this hydraulic diameter in this case is circle. So this is for round and this is for square. Now what about the hydraulic diameters? Okay, so hydraulic diameters is nothing but the flow rates. Okay, so if you see F into REH value is given, so F into REH, so what is Reynolds number? Rho fluid V average into D hydraulic by mu. This is F into REH. Okay, so how do you calculate the hydraulic diameter? So basically in case of a round cycle, the hydraulic diameter is nothing but D, because if you see the expression for hydraulic diameters, the hydraulic diameters are nothing but 4 times of area of cross section of flow. 4 times area of cross section of flow. This divided with area of cross section of flow divided with the wetted perimeter. So this term is very important, wetted perimeter. Okay, so this is wetted perimeter. Okay, so if you see this is the wetted perimeter, so this value is equal to, for this square, DH in case of square is equal to 4 times, look, it's given, it's completely has enough amount of material, so it is completely filled. So A square is the area of cross section for the flow divided by the wetted perimeter, which is 4 times of A, which is actually A, the length of side of the square. And of course for a circle, dh for a round or circle is actually equal to 4 times flow area, which is pi d square by 4 divided by wetted perimeter, which is pi d. So if you simplify this, you will get 4 gets cancelled, pi gets cancelled, and d this square gets eliminated. So this is d value. Okay, so that's how we have the hydraulic diameters for square and of course the round. Okay, so now if you substitute the expressions here, this v can be written as, the v which is here can be written as discharge divided by area of flow. Correct? So if you see, velocity can be written as discharge divided by area of flow. So let us substitute there. Okay, so let us substitute there actually. So if you substitute there, let's see what we'll get. So let us substitute there. Okay, so if you substitute here at this expression, of course the fluid is same, so OFG and OFG gets cancelled, and length of the stars is same, so length gets cancelled here. So when length gets cancelled, let us see, 2g is also common, so 2g and 2g gets cancelled actually. So f v square by dh, f v square, which is q by area of flow, which is a square whole square, divided by this dh term, which is small a, is equal to, for this square cross section, is equal to f into q by the flow area is 4 pi d square. Okay, so this is the flow area whole square divided by this area at, here this is diameter d for this circle. Okay, so this is for the circular cross section or the round, basically what you are telling. Okay, so this is round, this is actually round. Okay, so now let us see what these equations give you. So f into this quantity, so f into this quantity is this. So anyhow, let us see here. So if you see, we have this expression q square into f square by a to the power 5 of square is equal to q square times f into 16 by pi square d power 5. This is for a round. Okay, so this is the values. Now how f's can be equated? F's can be equated in this way. F can be written as, means this is the Reynolds number. So if this value is given as some value 56.9 something, so if this is given 56.9 something, then this f can be written as mu times of this quantity divided by density into average velocity, and this average velocity again you can write as discharge by flow area. So if you see in this case, this f into, let us write here, f into rho f into V average, which is nothing but q by flow area into hydraulic diameter by mu. So this value is equal to some constant. So let us call this constant 56.9 for example, which is given in this case. So if this is 56.9, now try to understand one thing. Can I write expression for f using all these conditions? Yes. So f is actually equal to how much? 56.9. Okay, f square is not there here, sorry. Yeah, only f is there. Okay, so f square is not there, only f is there here. Okay, so q square into f by a power 5 of square is equal to q square times of f into 16 by pi square d power 5. Okay, so now if you see this 56.9 times mu into flow area, which is a square, into flow area, which is a square, so mu a square by density of the fluid into discharge into this hydraulic diameter, which is a. So this is for the square, and similarly for the circle you have 64 into mu into flow area pi by 4 d square divided by density of fluid times q into this diameter d. So this is how we have the friction factors in both the cases. Okay, so if you simplify few terms, a and a gets cancelled, similarly here d and this d gets cancelled, similarly here this turns out to be 16 actually. So if you replace these quantities, q square by a power 5 into, what is the value of this f actually? If you replace this 56.9 56.9 into dynamic viscosity into A divided with this density of fluid times discharge at this section at the square is equal to Q square into 16 by pi square d power 5 into the friction factor in this case, which is 16 times mu into pi d by rho f into q. Correct? This is what you have. Okay, so in this case we have this 16 into mu into pi divided by rho f into q. This is for the round cross section. So if this is for the round cross section, now let us see some things here. Also you can cancel this d to the power 4 times here. Similarly this a you can cancel a to the power 4 times here. You can cancel one q, and here also you can cancel one q. And here in this case, in both the cases fluid is same, so mu and density gets cancelled. So if you see carefully, we have q of square q into 56.9 by a to the power 4 of square is equal to q into 16 square, and of course you can cancel one pi also here. So 16 square by pi d power 4 is there for the round. So from these two equations, if you see q square by q round, or what they are asking you, q round by q square, correct? So they are asking you in the question q round by q square. So if they want this value, q round by q square actually is equal to, means if you bring this q here and if you bring the other terms here, this gives you one equation, that q round discharge to the round pipe divided by the discharge to the square cross section is actually equal to, let us see what comes out. Okay, so 56.9 by a power 4, 56.9 by a to the power 4 multiplied with this pi d4 will come to this side as multiplication, and 16 square will go down. So pi times of d power 4 by 16 square. So this is the total value, and you know the relation between a and d we have already calculated by equating the parameters. A is equal to pi by 4 times of d actually. Okay, so if you replace a is equal to pi by 4 times of d and all, if you simplify, you will get the result. Okay, so please do this calculation. So let us do this calculation. A value can be written as pi by 4 times of d. So if you replace pi by 4 times of d here, pi by 4 times of d, pi by 4 times of d, so pi power 4 by 4 power 4 times of d power 4. Then this d power 4 gets cancelled. This 4 power 4 is same as this 16 square. So pi cancels you one time. So 56.9 divided by pi cube is what you have here. Okay, so 56.9 divided by pi cube is the term which is actually present here. Okay, so 56.9 divided by pi cube. Okay, so if you do this calculation, you will get the correct answer. So q round in this case by q square is equal to 56.9 divided by pi cube is what you have. Okay, so that's the value. Clear? So please type in the chat box, did you all understand how did we achieve this? 56.9 divided by pi cube. Okay, so did you all get this? Come on, type in the chat box. Got this value? All of you. Here we cannot substitute f as same for both the things, okay, because they have clearly given you f into this hydraulic Reynolds number is basically something, correct? Yes, little calculative, but you need to go for this. Okay, so 56 by pi cube, 56.9 something is also there, 0.9 divided by pi cube 1.835. So 1.835 is the quantity that is with you. Okay, the only thing, but we need to do the conversions little carefully, that's it. Okay, if you see, this is not actually very lengthy question, but of course you want to know this hydraulic diameters and you want to equate this pressures, that's it. Okay, this is simple relation by equating the parameters, and the main art lies in substituting this f values. Okay, so here we have done some analysis to know what are the f values, that's it. Okay, so that f values we have replaced, we have cancelled the common terms, and we finally ended up with this result. Clear? Okay, so let us see what is given. So D 1.83, of course. Okay, so 1.835 is the correct answer. So 1.83 is the taken as the correct answer here. Okay, this is actually one question which which is actually very important to you, because if you see, generally in this question we came to know what is the concept of the hydraulic diameter dh. Okay, normally in some pipes, in other cases, if you want a Reynolds number, you will directly write this formula with the diameter d here. But let us suppose when some square pipes or rectangular pipes are given, then in such cases, if you want to write a Reynolds number, this value is actually equal to the hydraulic diameter value, which is this. Okay, I'll tell you one very important thing about this guy, dh, hydraulic diameter. Okay, I'll ask you one question, you should tell me. Let us suppose if I give you a channel like this, for example, let us suppose there is a fluid flowing in this channel. There is a fluid flowing in this channel. Let us suppose if this length is A and if this length is B. Okay, then they asked what is the hydraulic diameter, and first option is obviously they have given you 2 times of AB by A plus B. This is what they have given you, which many of us feel that it is the correct answer, because 4 times of area of cross section, so 4 into A into B divided by the total perimeter, which is 2 times of A plus B, so 2 gets cancelled. So this is the first option. So even like at that time, after 4 years, earlier, I have also ticked this. Okay, I have kept this as the first option, I have ticked this and felt happy. But actually if you see this question, this 4 times of A into B actually is the cross sectional area, and but if you see, the wetted perimeter is only this much length of the solid is being wet by this fluid. Okay, here there is no solid that is being wetted by this fluid actually. Okay, so that's why when you are wetting this perimeter, this is only A plus 2B, but not 2 times of A plus B. This is the correct answer. Understood? Yes, so this is the correct answer, 4 times of A into B divided by A plus 2B. Okay, so this I have instead of this in overlook, I have written 4 times of AB by 2 times of A plus B, so 2 gets cancelled. I have written the same value 4 years back. Okay, and that time this question came in ISRO exam, and in ISRO, for every question you have plus 3 marks, and for every question you have minus 1 mark, and I missed ISRO with 1 mark in that year. Exactly within 1 mark I missed the cutoff, and that's it. Story is different. Okay, so that's why this hydraulic diameter sometimes is actually very important. Okay, clear? Fine. Okay, so shall we go for the next question? Yeah, it is slightly calculative because we need to find out the relation f between all these variables. That's the reason. Okay, so let's go for the next question. So let us see this question. Oil of density 800 kg per meter cube, dynamic viscosity 0.08 pascal second, is being transported through a 20 centimeter diameter 20 kilometer long pipeline at the rate of 3 pi liters per second. The power required to maintain the flow is K into pi kilowatts. The value of K is dash. Assume G is equal to 10 meters per second square and round off to 2 decimal places. Okay, this question is one very common question in oil transport industries like HPCL and IOCL, all these things. Basically you transport oil, and that's the approximate density of gasoline, which is your motor speed actually. So if you see petrol basically. Okay, so if you see, this oil is transported to a 20 kilometer long pipeline actually. Okay, and the flow rate is actually this much, 3 pi liters per second. But of course the diameters won't be like 20 centimeters, it will be some slightly higher pipe diameters. Okay, so the only thing that you need to maintain for the flow to happen is whatever is the pressure drop at some location by creating some pumps. Normally what happens in oil industry, I'll tell you, if you are transporting oil from one location to another location, because of the friction there is some pressure drop in the oil from location to location. So if you want to continue this flow, what you do is, between at some locations you have something called booster pumps. Okay, so what these booster pumps do is, they try to increase the pressure of the fluid again to the same initial point, and then again flow comes to some other point. Okay, so that's how if you want to transport fluid for 20 kilometers, it's not like there's a single, of course there's a single pipeline, but it's not like the fluid go in a single go. Okay, in middle in sections you have certain stations, piping stations, and also you have some booster pump locations, so that the pressure of the fluid is actually raised. Okay, so they are basically asking you what is the power required to maintain the flow. Correct? To maintain the flow, what is the power required? So obviously if you see, power required is equal to rho f g into the pressure drop per unit length. Okay, so means basically HL. Okay, so this is HL, rho f g times of this HL is basically the power that is required. Mass flow rate should be there. So mass flow rate rho F into Q. This is the mass flow rate into pressure drop per unit mass, which is delta P. If you multiply, then this is the total the power that you need to supply for the flow to happen, because this is the mass flow rate and this is your pressure, okay, pressure change basically for this pressure drop for this flow. So if you see this delta P value is nothing but we can calculate rho F G into HL, okay. So if you do that, we'll get the value of in kilowatts, okay. So this is rho F Q into delta P. Clear? So did you all understand basically how this expression turns out? This is the pressure drop, of course, and this pressure drop for multiplied with the total mass flow rate is the power that is required. That's why the discharge is also given here. So let us calculate this value. But to calculate this value, what are needed? You need this delta OF Q and this delta P. Density of the fluid is given. This discharge is also given, okay, 3 pi liters per second. Now the only thing that you need to calculate is this delta P. So let us see what is this delta P value, okay. So delta P is equal to density of the fluid times discharge into this delta P. So what is this delta P? Delta P, pressure drop per unit weight, is equal to how much? Delta P is equal to we have this rho F G into this head loss, which is FL V square by 2 GD. So if you simplify this, what you will get, rho F GG gets cancelled anyhow, rho F into F, basically friction factor. How you calculate the friction factor? Something is given to you, friction factor is given, not given, okay. So let us take 64 by Reynolds number. It's a laminar flow, let us assume. So 64 by Reynolds number, let us take, okay. So Reynolds number, and Reynolds number is nothing but into mu or into kinematic viscosity divided by V average into diameter, okay. So V average D by mu. So this is 64 times nu by V average into D. So V average can be written as V average is equal to discharge by flow area. So 4Q by pi D square is the value of V. So if you replace all these quantities here, so 64 times kinematic viscosity by V average, which is 4Q times pi D square. Okay, so this is the quantity 4Q times pi D square into D. So this is the friction factor value. 64 times kinematic viscosity, 4Q by pi D square is the velocity, into this diameter is the friction factor, right? 64 by Reynolds number value, okay. Shouldn't we calculate IE first? Yes, we are calculating directly in this expression, okay, because Reynolds number can also be written in terms of discharge and diameters. So we are calculating directly here, okay. So this is F value into L into again V square. So again V square can be replaced with this value, 16 times of Q square by pi square D power 4 into, so FL V square by 2D is there still, okay. So 2 times of this density, okay, so sorry, diameter, 2 times of this diameter, it's a pipe. And now if you see carefully, this density and kinematic viscosity, if you multiply, you can write dynamic viscosity value as usual, correct? You can write dynamic viscosity value. So 2 table cancels this 8 times and 4 table cancels this 2 times actually. So 2 times of 64, 128, okay. So pi, we have 1 pi here, so you cancel this square. Similarly, you have 1 D square, so cancel 1 D square here, okay. So cancel 1 D square. So you have Q also there, so you cancel 1 Q. So let us see what comes out. 2 times of 64, 128 mu, okay, and we have one more Q here, Q and L is also there, mu Q L by, there is 1 pi D square D, so total D power 4 pi D power 4, correct? So 128, 2 into 64 is 128, mu is there, L, Q is here in the discharge, so 128 mu Q L by pi D to the power 4. So please tell me, is this the expression for this pressure drop? So please tell me, can we calculate the pressure drop using this expression, 128 mu Q L by pi times of D power 4? Can we calculate this? Yes or no? So please type in the chat box, can we use this pressure drop expression as this function, 128 mu Q L by pi D power 4, correct? I think this can be calculated because we have substituted everything in terms of V average and all this. So now let us see. Therefore, power required is equal to how much? Power required is density of the fluid, which is 800 they have given you. So 800 is the density of the fluid, okay. So let us first write rho F into Q into this quantity. So 128 mu Q square L by pi d power 4. Okay, so this is the total value. Now if you have all the values, you can just substitute and get the answer. Let us see. Power required to maintain the flow is, density of the fluid is 800 kg per meter cube, 800 into 128 into dynamic viscosity. Dynamic viscosity is 0.08 pascals, so 8 into 10 power minus 2 into q square. The discharge is 3 pi liters per second. So if you want to convert this to meter cube per second, so 3 pi into 10 to the power minus 3, so square of that is 9 pi square into 10 to the power minus 6 into the length of the pipeline is how much? The pipeline length is 20 kilometers, so 20 into 10 cube. So this value divided by pi times of d power 4. So what is the diameter of the pipeline? 20 centimeters. Okay, so if it is 20 centimeters, then 2 into 10 power minus 1 meter, so 4, okay, 2 power 4 is 16 into 10 to the power minus 4 is the value here. Okay, so this is d power 4 value, because 2 into 10 to the power minus 1 is the diameter. So if you make it to the power 4, so 16 into 10 to the power minus 4. Now if you see, they have retained this pi here in kilowatts calculation. Okay, so let us see what comes out. If you simplify, this 2 zeros and this 2 zeros gets cancelled, and obviously this is 0 and this 4 zeros, total 4 zeros can cancel this 10 to the power minus 2 times. This 10 to the power minus 2 can cancel this 10 to the power minus 2 times actually. Okay, then you have this 2, so 2 into 8 can cancel this 16. This pi can cancel 1 pi here. So basically what you have, P is equal to 8 into 128 into 9 pi. Everything got cancelled by 10 to the power minus 2. By 10 to the power minus 2. So if you simplify this, let us see what is the value here. Okay, so pi they have retained as it is. So similarly, if you want to calculate the value in kilowatts, then 8 into 128 into 0.9 times of pi kilowatts. Okay, so let us calculate this value. That's the value which we need actually in this question. Okay, so this k value is basically equal to this value, right? Okay, after then only get flow is laminar or turbulent. Yes, but here turbulent relations are not given, so we are taking it to be laminar by default. Okay, first, if you actually speaking, you need to calculate the Reynolds number, and once Reynolds number is less than 2300, then we'll take the flow is laminar and we'll do all this analysis. But here no relation is given for the turbulent analysis, so that's why we are taking the flow to be laminar by default. Clear? Okay, so is that clear to you why we are taking directly the laminar flow? Fine, so shall we go ahead? So please type in the chat box, is this clear to you? We'll check the answer. What is the answer? But let us see. Did you all understand this calculation? So did you all get this calculation? P is equal to rho f times 128 mu q square L by pi d power 4 with this analysis. Okay, so once you get this, we'll see how to calculate now. Clear? So if you calculate now, I think we have substituted everything correct. 800 128 mu 8 into 10 power minus 2, this q square is 9 pi square into 10 to the power minus 6 and into 20 kilometer pipeline, so 20 into 10 cube divided by pi into 2 into 10 power minus 1, 20 centimeters, so power 4 is 16 into 10 to the power minus 4. So I think the values are correct. So if you substitute these 2 zeros and these 2 zeros gets cancelled, obviously, then this 4 zeros can cancel this 10 to the power minus 2 times, and 10 power minus 2 can cancel this 10 to the power minus 2 times here. This 2 and 8 mixing will cancel 16, and pi has cancelled this pi once. So if you see 8 128, then 9 into pi is here. All these terms got cancelled and divided by 10 to the power minus 2. So if you want this answer is actually in watts, so if you want it in kilowatts, you need to multiply this with 10 power minus 3. So we have this value, correct? Okay, so is every substitution correct here? So please confirm. And this formula is also very frequent used formulas here, right? Did we miss any quantity here? So please check. Rho f, so rho f into g into this f value is 64 by Reynolds number. Okay, so 64 nu by V average into d. So V average into D can be written as V average can be written as, you know, pi by 4 into q by pi by 4 d square. So 4 times of q pi d square divided by this hydraulic diameter d into mu, because this rho into this quantity we have it in mu, L V square. So V square is actually this quantity. So this is, if you cancel this d square here, we have 1 2d square and d. So total we have this d square, correct? So discharge missing, we have missed the discharge value, we have written here, right? So please tell me, we have written the discharge here. Yes, this q got cancelled, right? One time here, so we have only one q. Okay, so if you see, this q got cancelled here, so but this, if you see, we have only q. Okay, 128 mu q L, but this multiplied with this discharge again. Okay, yes. So please tell me, power value, if you see, power basically is equal to rho fluid G Q into this H, correct? So rho F G Q H. Yes? Yes or no? This expression is correct. So what we have made mistake here? Rho F we have considered, Q we have considered, this G into H. Okay, G into H means there comes a delta F here, correct? Yes or no? We'll calculate this delta F here. So this delta F cancels. Okay, so fine. Definitely we have missed this delta F here. Yes, we have missed this delta F here. So that's why there is this rho F in the bottom in all the terms. Rho F comes out here. So rho F comes out. So that means there is 800 here. So divided by 800. Okay, so this density is also there, correct? We have missed one density. Okay, we have missed one density actually, because you see power formula is rho F Q G H. So if you are converting this, you have a rho F term here. Clear? Yes. Normally in fluid flow cases, whenever I want to calculate the pressure variation, I generally go from the velocity profile. Okay, I used to apply integration and all, but since this time we are writing the formulas directly, we are missing some terms. Normally every time when I calculate in class, that by taking delta P is equal to, if I want to calculate the pressure difference, I will start from this equation. I'll start from this equation. Okay, so from this equation we'll start. Okay, so in this equation what we can do is, basically if you do the integrations between two values of lengths, actually by taking this r value 0 for example, then if you apply integration, you will get r square by 4 mu times change in pressure is equal to change in length and all these things. Okay, so anyhow, let us see. So here, if you see, if you divide this with 800, let us see what is the value. 8 into 128 into 0.9 into 0.9, this value divided by 800. Okay, so 1.152 by kilowatts. Okay, so this is the value, 1.152 times by kilowatts. Okay, so this value is 1.152, it should be, if I'm not wrong, 1.152 to 2 decimal places, so 1.15. So 1.14 to 1.16 is the correct answer. Okay, so basically we missed this density in the density in this location. Okay, because you see this is rho G Q H, so that's why if you see rho G, we have already this G into H can be written as delta P by rho. Okay, so because of missing this density here, this density gets in the denominator all over, so we'll get this expression 1.152. Okay, clear? Yes, 1.152 kilowatts times pi actually, but Bhavya, what they have asked you is, that is k is equal to 1.152. Yes, of course, k value is, if you check, you got k value is 1.152 in this case. Okay, this density is missed, that's the reason. Clear? Basically if you see, the power is basically the pressure difference that has to be maintained by the total discharge actually. So q times of this delta P, so that's why this 128 times of mu q L, and this density of the fluid also comes out here. Okay, fine. So let's go for the next question. So let us see this question. An oil of specific gravity 0.87 and kinematic viscosity nu is equal to 2.2 into 10 to the power minus 4 meter square per second flows through the vertical pipe as shown in the figure. The rate of flow is 4 into 10 power minus 4 meter cube per second. Then the manometric reading H is dash. So if you see, there is a manometric fluid like this. So this manometric fluid is of specific gravity 1.3. Okay, I think it is not visible, but actually let me write the data. So specific gravity of manometric fluid is 1.3 actually. Okay, so it is 1.3, and specific gravity of oil is how much? 0.87. Okay, now as shown in the figure, the rate of discharge Q is how much? Q is equal to 4 into 10 to the power minus 4 meter cube per second. Then the manometer reading H is dash meters. Okay, so then the manometer reading H is dash meters. So let's calculate the manometer reading here. Okay, so to calculate the manometer reading, definitely we need to identify the pressure difference at this location and also the pressure difference at this location. Means the pressure difference between these two locations, 1 and 2. Okay, because you see the manometer limbs are connected between these 2 points. Okay, so when the manometer limbs are connected between these 2 points, now let us check here. What is this manometric deflection? So let us apply the Bernoulli's equation, and of course this has certain friction factor also. Now since we are taking viscosity into the picture, there is some loss for this flow. Okay, so if you apply the Bernoulli's equation between points 1 and 2, so P1, so applying Bernoulli's equation at points 1 and 2, applying Bernoulli's equation at points 1 and 2, at points 1 and 2 actually. Okay, so if you apply this, let us see what happens here. P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2z plus Z2 plus head loss due to friction. Okay, so head loss due to friction. So now let us see what are the terms we can cancel out. Okay, so this is a pipe of uniform diameter, because if you see this is a uniform diameter pipe, so whenever this is a uniform diameter pipe, if you apply continuity equation, what is the relation between V1 and V2? So please tell me, if you apply this continuity equation between these 2 points, since the pipe is of some uniform diameter, then please tell me what is the relation between the locations of velocity at 1 and 2? They are same, correct? So V1 is equal to V2. Why? Pipe is of uniform diameter. Pipe is of uniform diameter. Okay, so pipe is of uniform diameter. Now, so that's why we can cancel these 2 terms. Velocities we can cancel. Now, the 2 points are separated by this datum, which is 4 meters. Okay, so they are separated by this 4 meters. So if they are separated by 4 meters, let us suppose if you take this quantity as 0, for example, if you take the potential this as 0, then this is 4 meters. Okay, so this is 4 meters. So if you want to calculate this difference, P1 minus P2 by rho g. So oil, of course, here the fluid is oil. So P1 minus P2 by density of oil times G is equal to HL minus 4. Okay, so what is HL value? That's what you need to calculate now. Okay, so HL is equal to, or you can write the pressure difference between these 2. Anyhow, we have to calculate HL. So HL is equal to FLV square by 2GD diameter. Okay, so since look, actually speaking, I have to calculate this Reynolds numbers and need to check whether the flow is laminar or turbulent, but since no turbulent relations are given here, I am just assuming the flow to be laminar directly. Okay, because turbulent relations are not given in this case, so that's why we are talking about this. Okay, so let us see here this F. So F is again 64 by Reynolds number. So 64 by Reynolds number, if you see, F value is equal to 64 by Reynolds number. So how do you calculate Reynolds number? V average into D by, okay, this is Reynolds number by kinematic viscosity. So into kinematic viscosity actually. Okay, so V average D by nu. So 64 by Reynolds number will give you this quantity. Okay, so how to calculate V average? V average is again given by this. V average can be given by discharge by flow area. Pipe diameter is given. Okay, so V average can be written by discharge by this flow area. So discharge by, what is flow area? Pi by 4 actually. Okay, so pi by 4 actually. Okay, so Q by flow area, let us say flow area, if you write into D, if you write, then this is flow area multiplied with QD. Okay, so 64 times kinematic viscosity into flow area divided by this QD. This is the friction factor totally. Okay, so this is the friction factor basically, right? 64 times this, and V average is Q by flow area into diameter. Flow area goes on to the top. Let us substitute here. So HL is equal to F, which is 64 times this kinematic viscosity into A flow area divided by Q into D into L into V square, which is again Q square by flow area square divided by 2GD. FLV square by 2GD. Okay, so if you simplify one thing, you have this Q cancels this one time and A cancels this one time. Okay, so if you multiply here, 64 times nu L and Q, we have these quantities here divided with 2G area into D square. Okay, so this is what you have, D square. Okay, so if you simplify this HL value, let us see, diameter is given, this Q is given, kinematic viscosity is also given. Kinematic viscosity is given directly, so kinematic viscosity is 2.2 into 10 to the power minus 4, and flow area, diameter might have also be given to you. So if you simplify this expression, let us see, 64 times kinematic viscosity. Kinematic viscosity is 2.2 into 10 to the power minus 4, so 22 into 10 to the power minus 5, let us write, into length of the pipe. So basically the distance between these 2 points is 4 meters, so this is 4 into Q. What about the discharge? Discharge they have given you 4 into 10 to the power minus 4. 4 into 10 to the power minus 4 is the discharge divided by 2. G they have asked you to take 10, right? Okay, that's in the previous question. Okay, nothing is given. So let us take 9.81. 9.81 flow area pi by 4. So this 4 goes to multiplication here, pi by 4 d square and one more d square, so total d power 4. So d is 20 mm, so 20 mm whole power, you know what do you have, this is d square and this is d square, so total d power 4 actually, correct? So d power 4 is 20 whole power 4 into this is 1 mm is 10 to the power minus 3, so total 10 to the power minus 12 is what you have here. Okay, so this is the total value of HL in meters. Okay, so let us simplify this. So can I find head loss any side? Yes, basically head loss can be calculated at the center, so that's why we are doing. Okay, so flow from up to down or down top, that depends upon the difference here. Okay, but since there is head loss here, so if you see there is this head loss, so it's a vertical pipe. So let us suppose if you assume this, let us suppose if HL is coming out negative value, that means flow is from up to down. Okay, it depends upon this head loss value. Now let us suppose if this value comes out to be some negative value, because if you see P1 minus P2 by OG is HL minus 4. Now let us suppose if this HL minus 4 value is it depends basically on this head loss value. Okay, if this quantity if I am getting to be negative, then basically since V1 got cancelled, it depends upon this piezometric difference, means P1 by OG plus 4 minus P2 by OG. So P1 by OG plus 4 minus P2 by OG, if you consider, we have this HL. Okay, so it depends on this summation P1 by OG plus Z1 and P2 by OG plus Z2, because velocities got cancelled. If this quantity actually is higher than this quantity, then that flow is actually from high to first point to second point. Okay, so it depends upon flow. Flow always happens from high energy point to low energy point. So this, if you calculate energies at these two locations and if you get this as the higher energy, then definitely flow happens from point 1 to 2. Okay, that's how actually we decide flow, the direction of the flow. Okay, so now if you simplify this, let us see what we get. Okay, so 10 power minus 5, 10 power minus 4, 10 power minus 9, so this cancels 10 power minus 3, so we have 1 10 power minus 1 here, again 10 to the power minus 1. Okay, simply if you cancel out again, we have 10 power 4 and 10 power minus 1, so cancelling this 0, I can write a 10 cube on the top, sorry 10 power minus 3 on the top here. Okay, so I can write 10 to the power minus 3 on the top. Similarly this 2 can cancel this 11 times. Okay, and what are the other conversions? 2 power 4 16, this 2 power 4 16 can cancel this 4 times actually. Okay, so 4 times you can cancel this, and I think that's how we have the relation for HL. HL is equal to, if you simplify this result, HL is equal to 4 into 11, 44, 44 into 16, so 44 into 16 by 44 into 16 and one more 4, so total 64, let us say 44 into 64, this value divided by then 9.81 times pi. Okay, so 9.81 times pi into 10 to the power minus 3, these many meters. So if you calculate this value HL, then let us see how you actually have this value. Okay, HL is equal to dash meter. So if you simplify this, 44 into 64, 44 into 64, this quantity divided with 9.81 times pi, 9.81 times pi. Okay, so this value 91.37 something 91.372 into 10 power minus 5 means 0.09 0.0914, you can say 0.0914. So how many of you got this value of HL? How many of you got this value for this HL? So please tell me. HL is 0.0914, correct? 9.137 or 0.0914 meters. It is the friction loss, correct? So please type in the chat box. Is this correct? We have to check the calculation actually. Okay. Must be 9.137. Is it? Did we skip any 10 power minus some quantity here? 44 into 64 divided by 9.81 into 10 to the power minus 3 is what you should get. 44 into 64. Okay, so 44 into 64 divided by 9.81 divided by 9.81 into, okay, divided by 9.81, just a second, 2816 divided by 9.81 divided by pi. Okay, so 91.37 is what you got, and multiplied with 10 to the power minus 3. 91.372 is what you are getting. What about the discharge quantity? We have this discharge. So 64 kinematic viscosity LQ by 2G AD square, correct? So if you see previous question also, we got this expression F is equal to 64 nu pi d square by 4 QD. So if you simplify this one more time, let us see. If you replace this A with pi by 4 d square, for example, if you replace this with pi by 4 d square, let us see what happens. We have some doubt in this, so let us check once again, because you're asking me to check this once again. So let me calculate this once again. Okay, let us calculate this once again. So if you calculate this value once again, this is equal to 64 times kinematic viscosity L into Q by 2G pi by 4. So this 4 goes here, pi by 4 d square into d square. So total d power 4 actually. Okay, so if you simplify this, 2 cancel this 2 times. So HL is equal to 2 times of 64, 128 nu LQ by pi G d power 4. Okay, so I think this is the same expression that we got, correct? So 128 nu QL by pi G d power 4. Okay, so that's what we got here. Yes, so please type in the chat box. Is this clear? FLV square by 2GD. So please tell me, is this the clear expression? Okay, so now type in the chat box. Is this expression clear to you? 128 nu LQ by pi G d power 4, correct? We have calculated everything correctly. So confirm this expression. We'll substitute the values now. So once confirm the expression, if the expression is correct, then we'll substitute the values. Okay. So yes, this expression is confirmed, correct? So 128 nu LQ by pi G d power 4, correct? This expression value is correct. So now let us substitute the values. Let us substitute the values. Let us see what happens here. So if you substitute the values, then let us see what comes out here. HL is equal to 128 times of this kinematic viscosity. Kinematic viscosity is 2.2 into 10 power minus 4. So 2.2 into 10 to the power minus 4. Okay, so 2.2 into 10 to the power minus 4 here. Okay, so expression correct, right? Expression is correct. Now let us see here. 2.2 into 10 power minus 4 into next LQ. So what is L? This is 4 meters. So L is 4 meters into Q. Q is how much? 4 into 10 to the power minus 4. 4 into 10 to the power minus 4. So this value divided with pi G d power 4, correct? So pi 9.81 d power 4. So what is diameter? 20 mm, correct? So this is 20 mm. So 20 mm power 4. So 20 power 4 into mm into meter cube is 10 to the power minus 3. So 10 to the power minus 12 totally. So this is 10 to the power minus 12. I hope now it's correct, right? So let us simplify this. If you simplify, what is the answer? This is 10 to the power minus 8 and this 0 will give you one more 10 to the power 4. Okay, so this 10 power minus 12 gets cancelled in this value. So 2 power 4, 16. So 16 and 4 cancels 4 times and this 4 and 4 gets cancelled. So no more terms here. So if you see 128 into 2.2 by pi times of 9.81. So these many meters. Clear? So let us calculate this value. 128 into 2.2. 128 into 2.2 divided by pi times of 9.81 divided by pi times of 9.81. So if you simplify this, 9.1372. Yes, 9.1372 is the head loss actually. Okay, so this implies your P1 minus P2 by density of oil times G is equal to this value minus 4, which is 5.1372 meters. Okay, so P1 minus P2 by density of oil times gravity is equal to 5.1372 meters. Yes, so 9.137 is basically correct. Previously we have computed some 10 power minus 1 mistake somewhere, so that's why, but this is the correct value. P1 minus P2 by oil G is equal to 5.1372. right? Now this same pressure difference means P1 minus P2 value is how much? P1 minus P2 is given by density of oil times G into 5.1372. So this is the pressure difference between the 2 points. Clear? So if this is the pressure difference between the 2 points, P1 minus P2 is equal to density of oil times G times of 5.1372. So this pressure difference is nothing but the pressure difference which is shown by this manometer. The pressure difference which is recorded by this manometer. So what is the pressure difference that is recorded by this manometer? If you see, this is nothing but the pressure difference due to this column of manometer, right? This is H. Okay, so now if you see, let us calculate the pressure difference with this manometer. So if you see, this complete water column and this complete water column always gets cancelled. So the pressure difference between these two is nothing but rho of this manometric fluid minus density of this oil into G into H. Yes or no? So please tell me, the pressure difference between these 2 points is nothing but the pressure difference due to this manometric deflection, which is given by density of this oil, density of this manometric fluid minus density of oil times G into H. Correct? Yes? So type in the chat box, is this correct? Okay. So type in the chat box, is this value correct? So we have got the difference between pressures P1 and P2, and this P1 minus P2 value is actually equal to, if this is H, then density of this fluid minus density of this density of this manometric fluid minus density of this fluid into G into H. Correct? Because if you apply the hydrostatic law, because if you see, this is a manometer, so if you apply the hydrostatic law at this point, about this point, okay, so about this point, if you apply the manometric law, so P2 minus this water level plus P2 at this level, so this is the pressure. So if you see, at this location, the pressure is given by P2. If this is location A, if this point is location A and if this point is location B, then from the principle of manometry, since this complete fluid is actually in static condition, then definitely pressures at these 2 locations should be same. Okay, so how we actually calculate them? So see here, PA is nothing but P2 minus this density of fluid plus this density of this oil. Okay, and here if you see, this is the complete column of this oil basically. So the pressure difference between these two is density of this oil minus density of this fluid times G into H. Correct? So if you see PA, let us write the hydrostatic equation. PA is equal to P at location 2 minus P at location 2 minus this difference due to this this point is 4 meters and this is H. So okay, directly we can write, so this difference is equal to P1 minus P2 can be written as density of manometric fluid minus density of this oil times G into H value. Okay, so you have this value of P1 minus P2 and you have this value of P1 minus P2 from the manometer. So if you equate both of this, you will get H value. So please type in the chat box. H equal to 3.438. Okay, so let us see. H equal to 3.438, but this value is something different. I think the key got mismatched during typing because we have ticked the questions actually for the DTP operators, but I think the key got changed actually. Okay, I think this key was shifted because I think for 2-3 questions the key got shifted. So I think actually they have shifted the key, means they have entered the wrong key. Somewhere numbers got mismatched, but right now if you check the calculation, yes, H value should be some few meters, and I think your calculation 3.438 is actually correct. 3.438 meters if you equate these two. This is the correct 3.438 meters, the manometer reading. Okay, so if you have 4 meters, this is a big manometer, so 3.438. okay, yes, so 3.438 meters could be the manometric deflection. Clear? Yes, this value is correct. Maybe during the typing they have entered the wrong key, because key gets shifted sometimes when question numbers are not looked properly, but this is the correct answer because it's obvious. Within a 4 meters manometer you cannot have 17 meters deflection. Okay, this manometer is connected between these 4 meters, and if you see, then this deflection cannot be if you see, this deflection is almost somewhere close to in between these 2 points, so that's why it cannot cause 4 in general. So 3.438 is correct answer. Okay, there is some key typing issue here. Fine. So please type in the chat box. This H is equal to 3.438 meters is the correct answer in this case. Okay, so let's go for the next question. Let us see this question. Two fixed horizontal parallel plates are spaced 1 centimeter apart. A viscous fluid having mu is equal to 0.4 Newton second per meter square flows between the plates with a mean velocity of 0.15 meters per second. If the flow is laminar, then the magnitude of pressure drop per unit length. So pressure drop per unit length, which is nothing but pressure gradient. For 1 unit length, what is the change in pressure in the direction of the flow is in kilopascals per meter is dash. So let us see, they have one plate. Okay, and this plate is like this, and two fixed horizontal plates. Okay, so two fixed horizontal plates. So let us take, these are two fixed horizontal plates. These are two fixed horizontal plates. These are two fixed horizontal plates. Now whenever these are two fixed horizontal plates, they have given how much is the distance between them, are spaced 1 centimeter apart, means basically this distance is 0.5 centimeters. H value as per our nomenclature is H is equal to 0.5 centimeters. Okay, so H is equal to 0.5 centimeters. Now if H is equal to 0.5 centimeters, then let us see what are given. The dynamic viscosity of the fluid is 0.4 Newton second per meter square. So dynamic viscosity of the fluid is 0.4 Newton second per meter square. Okay, now let us see this case. And mean velocity of 0.15 meters per second. So u mean is equal to 0.15 meters per second. Okay, so u mean is equal to 0.15 meters per second. Magnitude of the pressure drop. Okay, so magnitude of the pressure drop, I told you for this case, if y is measured from here, let us suppose, then the velocity function is given by h square by 2 mu times minus dp by dx times of 1 minus y square by h square. This is the function for this velocity. Correct? I have given you this expression in the beginning today. Now if you want u maximum velocity, then definitely when plates are fixed, maximum velocity will lie at the center, and the location of the center is basically y is equal to 0. So if you replace y is equal to 0, the velocity what you get here is actually the maximum velocity in this case. Okay, so this implies u max is equal to how much? H square by 2 mu times minus dp by dx. Okay, so this is the relation, h square by 2 mu times of minus dp by dx, because if you replace y is equal to 0, the velocity what you get here is the center line velocity, which is the maximum velocity, and this maximum velocity is actually equal to 2 times u max is equal to 2 by 3. Correct? So u max by u average is equal to 3 by 2. You can write, okay. So this is 3 by 2. So if you want to write this u maximum in terms of u average, this u max is nothing but 3 by 2 times of u average, okay. So 3 by 2 times of u average is equal to h square by 2 mu times minus dp by dx, okay. So this is the pressure gradient value. So if you simplify this result, then 2 gets cancelled, of course, and we want this magnitude of this dp by dx. So let us calculate what is this value of minus dp by dx. So this implies minus dp by dx is equal to, how much is the value? 3 times of u average into mu by h square. So 3 mu u average, which means u mean velocity, by h square. So let us simplify the values. 3 times mu dynamic viscosity, 4 into 10 to the power minus 1, average velocity, which is mean velocity, 15 into 10 to the power minus 2, divided by h square. So h square, this value is in centimeters. So if you convert that to meters, this value in meters is 5 into 10 to the power minus 3 meters, okay. Because if you see 0.5 centimeters, so 5 into 10 to the power minus 3 centimeters, okay. So if you replace this h value here, 25 into 10 to the power minus 6, okay. So 25 into 10 to the power minus 6. So if you simplify this value, your answer is going to be in pascals per meter, okay, because pressure gradient per unit length, so pascals per meter, because we have substituted everything in SI units, okay. So now if you simplify this, let us see. If you simplify this, 10 to the power minus 1, 10 to the power minus 2 gives you 10 to the power minus 3 here, okay. And this value 5 table 3 times, 5 table 5 times. So 3 3s are 9, 9 4s are 36, 36 by 5. And what are the units they are asking you in? They are asking you in kilopascals per meter. So if you want kilo, then definitely this 10 power minus 3 can be neglected then by putting a k here, okay. So 36 by 5 kilopascal per meter. So this is some kilopascals per meter. So if you simplify this, 36 by 5 gives you 36 by 5 gives you 7.2 directly, okay. So 7.2 kilopascals per meter, clear. So that's the pressure difference basically between per unit length of the flow, actually, clear. Yes, 7.2 is correct answer, correct. 7.2, Tripathi, Abhimanyu, Bhavya, all of you guys. So 7.2 is correct answer for this question, okay. So basically you can write all these expressions if you know this velocity profile, okay. So since I'm not doing the things directly, we are writing this velocity profile, we are not deriving this, so that's why I have given you this velocity profile for this nomenclature initially, okay. So 7.2 kilopascals is the kilopascals per meter is the pressure difference, means for 1 meter of the flow, the pressure drop in the flow is actually 7.2 kilopascals, clear, okay, fine. So what is the answer given? 14.3 is given. Why? 7.2 is correct, right? So please type in the chat box. Did you all get 7.2? I'm getting 7.2 actually. So did you all get 7.2 here? Okay. So 7 point, yes, we are correct. 7.2 is the correct answer, okay. So as I told you, they have jumbled some key somewhere, so that's why all the answers given here are incorrect. So 7.2 kilopascals is correct answer, okay. I think during the marking of the question some key got jumbled maybe, so that's why they have entered some wrong key for all the questions, but anyhow this is the correct answers, okay. So now let us see this. An oil of viscosity 10 poise flows between two parallel fixed plates again, which are kept at a distance of 50 mm apart. If the drop of pressure in a length of 1.2 meters be 0.3 Newton per centimeter cube, okay, in a length of 1.2 meters is 1.3 Newton per centimeter cube, okay. If the width of the plates is 200 mm, width of the plates is given, then the rate of flow of oil between the plates is dash liters per second, okay. So we have the velocity profile. Once we have the velocity profile, if you want discharge, we can easily calculate, okay. So let us see how we can calculate. This is again the case of flow between fixed plates. So flow between fixed plates, flow between this fixed plates. If you take this coordinate as h, for example, okay, so this is the y direction, and let us suppose this gap between these two plates is h, and for any location y, the velocity is given by h square by 2 mu times minus dp by dx into 1 minus y square by h square, okay. 1 minus y square by h square. Okay, so they are asking you about the discharge. Then the rate of flow of oil between the plates is dash. Look, can I tell you one thing? If I say something, let us suppose if I tell you this, discharge is actually equal to average velocity into flow area. Correct? Can I write this into area of flow? Area of flow, which means in this case I can write this discharge as U average velocity into area of flow. I can write as 2h into width of the plates, which is 2h into W. Can I write this expression? So please tell me, can I write this expression value? Because discharge through any section is actually equal to discharge is given, or what they're asking you, the rate of flow of oil in liters per second. So they're asking you something about discharge. So if I want to write discharge, can I write this as average velocity times the flow area? Yes, I can write this value. Correct? So average velocity in terms of maximum velocity, if I write this is equal to 2 by 3 times of U maximum into 2h into W. So total this value is equal to the discharge that is flowing is equal to 4 by 3 U maximum into h into W. Okay, so h into W is the values. Now what is U maximum? You know, U max is at y is equal to 0. Okay, U max is at y is equal to 0 actually here. Okay, so U max is at y is equal to 0. This implies U maximum is equal to h square by 2 mu times minus dp by dx. Minus dp by dx actually here. Okay, so this is minus dp by dx. So let us substitute here. So if you substitute here, discharge is equal to 4 by 3 times of h square by 2 mu minus dp by dx into h into omega. So if you simplify this expression, we get, you know, 2, this is 2 times, so q is equal to 2 by 3 mu, let us say 2 by 3 mu h cube into omega, sorry, h cube into W, width of the plates, into minus dp by dx. So this is the total value for the discharge. So q is can be written as this value. So out of these quantities, what should be known to us? Dynamic viscosity value. Dynamic viscosity is how much? Dynamic viscosity is equal to dynamic viscosity 10 poise. So 10 poise and 1 poise is 10 to the power minus 1. So total it is 1 Newton second per meter square. Next, H value. So what is the clearance? They are kept at a distance of 50 mm apart. So if this is 50 mm apart, then if this is 50 mm apart, 50 mm, half of 50 mm is basically 25 mm. So 25 into 10 to the power minus 3 meters is the H value. H value is 25 into 10 to the power minus 3 meters. Then what about this, what they have given you? W, width of the plate. Width of the plate is how much? 200 mm width. So W is equal to 200 mm. So 2 into 10 to the power minus 1 meters. Then what about the pressure gradient? So it's given the pressure, if the drop of pressure in a length of 1.2 meters be 0.3 Newton per centimeter cube. Is it? Pressure drop is always in centimeter square, right? This is centimeter square, I think. Okay, so this is centimeter square. Within 1.2 meters length, the drop in pressure is 0.3 Newton per centimeter square, because drop of pressure has same units as pressure. So maybe it can be Newton per centimeter square. Maybe some typing, error. So 0.3 Newton per centimeter square. Okay, so now if you convert this drop in pressure, delta P by L, which is nothing but dP by dz, because it's a constant pressure gradient. So 0.3 Newton per centimeter square. So if you convert this to meters, this value divided by 1.2. So this is 4. So because if you see 4 times of 0.3 is 1.2. So 10 power 4 by 4 Newton per meter cube. Correct? So this is the value. So 10 power 4 by 4 Newton per meter cube. Yes? Yes or no? This is centimeter square, right? Because drop of pressure has same units as that of pressure. Okay? Pressure drop is having same units as that of pressure, right? So it's basically I think there is some centimeter square here. So 10 power 4 by 4 Newton per meter cube. Okay, so let us see, simplify the value what we have. So 10 power 4 by 4. So delta P dP by dx value. If you see, this value is how much? 10 power 4 by 4. So let us substitute all these values. Okay, so 2 by 3 into dynamic viscosity value 1. So anyhow 1 into h cube. H cube is basically 25 cube into 10 power minus 9. 25 cube into 10 to the power minus 9. This is h cube into W. 2 into 10 power minus 1 into the pressure gradient, which is 10 to the power 4 by 4. 10 to the power 4 by 4 actually. Okay. So if you simplify this result, we can get 10 to the power 4 can cancel this 10 to the power minus 5 times, and anyhow you can go for some other calculations also, but directly let us see what is the value in meter cube per second. Okay. So let us calculate the value in meter cube per second. Okay. Pressure drop for unit length, but they have given clearly that pressure drop of in 1.2 meters length, the pressure drop is this much. Okay. So that's why maybe some units they have converted from centimeters kVA to cube they have typed. Okay. So let us see here, 2 into 25 cube. 25 cube into 2. 25 cube into 2. Okay. So 25 cube into 2 into one more 2. Okay. So I think this 2 and 2 can cancel this 4 anyhow. I'm sorry, I didn't check this. So 2 and 2 can cancel this 4. So if 2 and 2 can cancel this 4, then 25 cube by 3. That's it. Okay. So 25 cube by 3 into 10 to the power minus 6. 25 cube by 3 into 10 to the power minus 6. Into 10 to the power minus 6. So 0.00520. 0.00520. So if you want this in liters per second, because they are asking you the question in liters per second, so definitely this value is nothing but, if you multiply by 1000, 5.2 liters per second. Okay. So this question is 5.2 liters per second. Okay. So 5.1 to 5.3 is the range for this question. Okay. So 5.2 liters per second is the discharge between these two plates. So which can be calculated using this simple expressions. Okay. Otherwise, what you have to do, you need to integrate this. Understood? Integral u dy into w from minus h to h. Rather than that integration, this conversion is very simple. Okay. So that's why, without actually doing the integration, since we know this relation that u average is equal to 2/3 of u max, we have calculated directly. Okay. Clear? Fine. So please type in the chat box, is this clear to you? So let's go for the next question. Oil flows between two parallel plates, one of which is at rest and the other moves with a velocity u. Okay. So if you see, it's the case of the other one. So you have a fixed plate and the other is moving at some velocity u. Okay. So the other plate is moving at some velocity u basically. Okay. So this is moving at some velocity u, capital U. This is capital U. Okay. If this is capital U, if this plate is fixed, then let us suppose the gap between the two plates is h. So this is the y direction. So this is the y direction and this distance is h. This distance is h. Now if the pressure is decreasing in the direction of the flow at the rate of 5 pascals per minute, means dp by dx is minus 5 pascals per minute. Okay. Because this is given it is decreasing. So that's why when x is increasing, this value can be taken as minus 5. Dynamic viscosity is 0.05 kg per meter second. So mu value is 0.05, means 5 into 10 power minus 2 kg per meter second, which is same as 5 into 10 to the power minus 2 Newton second per meter square. Okay. Newton second per meter square. Now the spacing of the horizontal plate is 0.04 meters. So spacing is how much? 0.04 meters. Then, and a volumetric flow per unit width. So W equal to 1. So Q is equal to 0.02 meter cube per second. Okay. 0.02 meter cube per second. So Q is equal to 2 into 10 to the power minus 2 meter cube per second. Okay. So this is the values. Then the velocity is dash. So basically what is the value of this u? That's what they are telling you. Okay. So I have given you directly one expression for discharge. Okay. So I have given you directly one expression for the discharge. Okay. So what is the expression for the discharge? Q is equal to u infinity or u into h into 1 by 2 plus this alpha by 6. Correct. So pressure value is given, dp by dx is minus 5 Pascal per meter. Of course, it's a very small value, but let us still consider that. Okay, so H alpha value. Let us calculate this alpha value. Alpha is how much? Alpha value is H square by 2 mu u infinity times minus dp by dx. Correct? So let us calculate this value. If you calculate H square is how much? 16 into 10 power minus 4 by 2 times mu. Mu is how much? 5 into 10 power minus 2 into u infinity, which is capital U, times minus of this value minus 5. So total plus 5. Okay, so this plus 5 and this plus 5 cancels. 2 cancel this 8 times. 10 square will cancel this 10 power minus 2 times. So alpha value is 0.08 by u. Okay, so u times q. Q is how much? 2 into 10 power minus 2. So 0.02. Let us say 0.02 is equal to u. H is how much? 4 into 10 power minus 2. 4 into 10 to the power minus 2. Let us write this q value also as 2 into 10 power minus 2. Then 10 power minus 2 gets cancelled. H, u into h into 1 by 2, 0.5 plus alpha by 6. Alpha value is 8 by u. So 8 by 6u. Okay. So 0.08 is 8 into 10 power minus 2 is here. Correct. So 0.08 by u. So 0.08 by 6 times of u. So this is the velocity. Okay, so if you need to calculate this equation, simplify this equation to get the value of capital U here. Okay, so if you calculate, you can get the answer directly. So if you simplify this, this gives you 2. So this implies 1 is equal to 2 times of u times, or if you multiply this 2 to the terms inside, we'll get u into 2 times of 0.5, 1 plus 2 and gets a 3 here. So 0.08 by 3 times of u is what you get. Okay, so if you bring this u to the bottom, 1 by u minus 0.08 by 3u is equal to u. So this implies 1 minus 0.08 by 3 is equal to u square. Okay, so this is the expression for this velocity u. Okay, so 1 is equal to, or 1 by u is equal to 1 by u is equal to here it is 1, correct? So this is 1 here, so the square don't come. Okay, so this is 1. So 1 by u minus 0.08 by 3u is equal to 1. So 1 minus of 0.08 by 3 is equal to u actually here. So if you simplify this, you can get the answer 0.08 by 3. This has to be subtracted from 1. So 0.973. 0.973 is the correct range. 0.973 meters per second is the flow, is the plate velocity at the top. Okay, so this u is equal to 0.973 meters per second is the velocity. Okay, so let us check the answer. 0.95 to 1.05. Yeah, of course, because if you see, this value is generally small, so if you neglect this, as you told, this value comes out to be 1 meters per second. Okay, but let us suppose if a range is given something like 0.95 to 0.99, in that case, then you'll face some problems. Okay, so until and unless they tell you, don't neglect the pressure gradient values. Okay, of course, I understand they might be very small, but still don't neglect them by default. Okay, clear? So as long as they tell you to neglect the pressure gradient, please don't neglect. Okay, because sometimes what happen, they give you the range from 0.95 to 0.99, something like that. Okay, for accuracy purpose. So then in that cases you will be in trouble. Okay, so don't neglect these values directly. So I think we have one more question. So if you see, oil of specific gravity 0.9 flows at 11.30 liters per second through a 75 mm diameter horizontal pipe. If the pressure drop for 300 meters length of the pipe is 415 kilopascals, then the viscosity of the oil directly. Okay, they have given everything, pressure drop and all. So pressure drop values and all is given. So they are asking you for the viscosity of the oil. Till now we have derived that formulas, 128 mu LQ something is there. So that if you apply, you will get the answer very easily. Clear? So will you do this question? So please type in the chat box. Shall I leave this question to you? Can you solve? Because in today's session we have done this question many times actually. If you see, the pressure drop values are known, then we will convert the formula that HL is equal to 128 mu QL something is coming, right? So let us see what is that formula we are getting. HL formula. Okay, so HL is equal to 128 kinematic viscosity LQ by pi g d power 4. If you apply this, you will get this 128 HL is equal to 128 nu q L by pi g d power 4 is what you are getting, correct? This is what you are getting, 128. Let us check, 128 nu LQ by pi g d power 4. Okay, so this value is nothing but delta P by rho g. So if you bring this L here, this rho g can be multiplied to the other side. So rho fluid g times 128 nu q by g d power 4. This is the expression. Okay, so if you simplify this, then gg gets cancelled. This density into kinematic viscosity can be written as dynamic viscosity. So delta P. So what is delta P given? 415 kilopascals. 415 kilopascals by length. What is length of the pipeline? Over 300 meters length. So 300 meters is equal to this density into kinematic viscosity will write dynamic viscosity, which is actually needed in this question. They are asking you the dynamic viscosity value in Newton second per meter square. Then 128 into Q. So what is Q basically here? Q is 11.30 liters per second. So 11.3 into 10 to the power minus 3 meter cube per second by diameter to the power 4. Okay, so diameter to the power 4, if you take 75 mm diameter, so 75 to the power 4 into 10 to the power minus 6. Okay, so this is the total calculation for this question. Okay, so d to the power 4, correct? So d to the power 4 means this is 12 actually. So you need to simplify this value to get the value of mu. Okay, 0.095 you are getting. Okay, so of course maybe you can get that. So if you simplify 10 to the power minus 9, okay, then these two zeros will make this 10 one time. Okay, so mu is basically equal to 4150 into 75 power 4 into 10 to the power minus 9 divided by 3 into 128 into 11.3. Okay, so if you simplify this, you will get the answer. Okay, so this can write 10 power minus 8 actually. So anyhow, if you simplify, let me use this 415 into 75 power 4, 75 power 4, this value into 10 to the power minus, first of all let us divide this, divided by 3 into 128 into 11.3. okay, so 11.3. So this value if you simplify and divide it with 10 power 8, so divide it with 8 10 power. Okay, so 0.0302 is what you are getting, correct? Okay, right, that's what you are getting, correct? So 415, everything is fine. So your answer that you are going to get is in Pascal second basically. Okay, you all are getting 0.095. Pi is missing. Okay, yes, pi is also there, right? So there is one pi here also, so multiply a pi here obviously, so pi should be there. So if you multiply a pi to this answer, then 0.09506, 0.095 Pascal second. Okay, that pi is also there. Yes, pi should be there, that pi also is there. Clear? So you might have observed one thing, generally people try to remember this formula, some 128 what is coming, yeah, 128 nu q L by pi g d power 4. I think there is also one more formula with some 32, I think, correct, if you remember. But generally, of course, during teaching of the class, even I teach that if this is given 32, we have some short formulas and all, but honestly speaking, all these formulas are not very much easy for you to remember. Okay, so that's why whenever I need something about friction factor or head losses, I go with this formula FLV square by 2GD, which is the constant, from that only all these formulas comes out. Okay, if you write F as 64 by Reynolds number, again writing Reynolds number as V average D by dynamic this kinematic viscosity. So by writing all these things, you will come to all these formulas actually. Clear? So my suggestion kind of thing is never go for some direct remembering of formulas, because if you miss one d square or d cube, or instead of square if you substitute cube, then you'll always get some different answers. Clear? Okay, yeah, in today's class there is some typing that caused some trouble to us in between, but I hope you understood how from the basics, from the Bernoulli's equation, from FLV square by 2GD, how we have wrote different things actually here. Okay, so in tomorrow's class we will talk about one very important topic, which is the boundary layer theory, which is basically the external flows of viscous fluids. Okay, so we will talk about that external flows of viscous fluids. We'll talk about the concepts of lift, drag, all these things. Okay, and yeah, that's how we'll basically take tomorrow's session, external viscous flows. Okay, today is the 6th lecture, so tomorrow we have the 7th lecture, so we talk about external flows. Okay, and I think yesterday night you have seen the launch of Gatopedia. So we have launched about this short notes for this gate mechanical, and of course for all other branches as well. So you see, this is one very important and very good opportunity for you, because if you see, short notes is, of course, if short notes is written by you, it's much more advantageous for you. But right now, since there is no time, we have provided you some short notes, so that if you definitely go through these short notes, every topic and every line in that book is actually written by the faculties, but not by someone else. Okay, so our team has completely sat there and designed that short notes book. Okay, so that's why if you see, every single point is going to definitely help you out very much in this upcoming gate examination. Clear? So please go for that short notes. You can download a copy probably from the PW app, and I hope in yesterday's session people might have shown you how to download that copy and all, our team members. So definitely make use of it, download a copy of that, and try to get benefit out of it. Okay, and of course very soon test series is also being launched, hopefully in the next week or something like that. The test series is also being launched, so if possible, try to get some subscription of that. It's I think very minimal price they are putting, like how the courses are being put at some very less price. Similarly, test series is at much lower price, so if you get it if you get the chance, definitely subscribe to the test series and start attempting the questions. Okay, because we are not copy pasting questions from anywhere, we are preparing the questions at our own. Okay, so definitely that test series will definitely help you out to a very good extent. Okay, so this test series and this short notes combination is going to help you very much in this gate examination, upcoming gate examination. Clear? So with this, we'll conclude today's session, of course, and we'll meet tomorrow at 11 AM to see the concepts of boundary layer theory. Okay, and of course lift and drag as well. Clear? Got it? Okay, yes, test series is already on the way. Okay, we'll about to launch it. Clear? So my main motto of this session is to tell you that you need not remember formulas. If you start working from the basics, you will get the answers very simply. Okay, and of course these are actually some questions which are more than the level of gate examination, but actually in gate you'll get very simple questions, and they can be solved very easily. In all these classes we are solving very high level questions. We have seen that for past few days, in past 5-6 lectures, and also today we have seen normally questions at this complexity, they generally don't come in gate examination. Okay, but if you solve these questions, you will have all the knowledge which is required to solve the actual gate questions. Okay, clear? So fine, shall we wind up this session now? Okay, so we are winding up this session then. Thank you all. We'll meet tomorrow again at the same 11 AM on the same channel to discuss questions on this external flows. Okay, thank you all. Thank you.